Thanks everyone for joining us today. I'm Prasanna Balaprakash. I'm a computer scientist at Argonne, and I'm pretty excited to present our work on automated machine learning package for deep neural nets. Also, the abstract sort of said it's a hyperparameter search package. What we are targeting is both hyperparameter search and neural architecture search, which are sort of the critical components to automate the design and development of deep neural nets. So I'm going to talk about that. I'm going to focus on both of them. So the way that I structured today's talk, first I'm going to give a high-level overview of both hyperparameter search capability of DeepHyper package and neural architecture search. And then I will show some examples, some online examples how to do that. So it's pretty easy to get started. You can even experiment on your own laptop before getting into Theta, and it is available as a module on Theta. So whatever you do in your single node machine on your desktop, you can scale it up easily on Theta, for example. Okay. So first and foremost, I would really like to acknowledge and thank the team behind DeepHyper. It's not without the effort of Roma, who was working with me over the last 1 year, and Misha at ALCF. The DeepHyper would not be possible, or would not be in a state which is in the current form usable for the users. So these two guys did a fantastic job of pushing things. And Stefan and Venkat gave a lot of inputs on the algorithmic development. So I would first like to thank our team behind DeepHyper. So motivation, this is an example from Google Neural Network Playground. So if you go to the Google TensorFlow Neural Network Playground, you can experiment with neural networks. Okay, so it's a very visual thing, and what you can do is you can set some number of features and then number of hidden layers, and we have an output. So this is a classification task. So what you see here, this is how this is a spiral data set, and you want to classify the spiral data set. And what you can do is just go and change the number of neurons in each of these layers. Instead of 4 neurons, you can do 3 neurons, and so on and so forth. So this is one particular configuration of a neural net for the batch size 10. So you see the batch size 10, and this is what the result you get. And you go and change so you see now you go and change the number of neurons. See how the classification accuracy changes, right? So just by changing the number of layers, or number of units per layers, the accuracy for this simple neural network changes a lot. So so this is another the same example but different configuration. So so this is the sort of the crux of the problem. Neural networks are very, very powerful, especially deep neural networks are very, very powerful given enough data. But coming up with the right neural network is always a challenge. And to say this, in an ideal scenario, this is what happens. You design a neural network, so you see whether it works well on the training data. If it is not, you go and increase the model complexity. You go and increase the number of hidden layers, number of unit per layers, and so on and so forth, and then see if it works on the training data well, which means that it learn on the training data. It learn on the training data and check if it is working on the testing data. If it is not, providing the other caveats like if it doesn't overfit and so on and so forth, then go and collect more data and iterate this loop, and then finally you are done with the desirable accuracy, and but this is ideal world scenario, and most often this is not the case. You have to always tinker around like how to find the right batch size, right learning rate, right optimizer, and so on and so forth. So these are the different hyperparameters. And sometimes you want to come up with the architecture itself. If you are dealing with images, perfect. There are convolution neural networks, and that's a good starting point. If you are dealing with a language, then you already have BERT type models that are being the state of the art. It's better to start with those type of things. Right? In many cases, the data that we have are not just text and images, right? So it's a series of inputs, and we have to predict the output. So surrogate modeling, a lot of simulation-based studies, climate simulations, weather forecasting, and transportation, and so on and so forth. So this is a series of inputs coming in, and we have a series of outputs, and we want to build models. So there is no sort of a blueprint that will allow us to do that. And in those cases, it's often like, it's a magic, or, for beginners, it's why neural network work, it's a magic. But for experts, it's more like, okay, it's art of building the right neural net. And more than 60 to 70% of the time, building the right neural network, the time to develop the model just goes in this trial and error process, trying to identify what is the right model, what is the right learning rate, what is the batch size, and so on and so forth. Okay, so to address this problem in the design and development of deep neural net, what we have developed is this package called DeepHyper. DeepHyper is a scalable automated machine learning package for developing deep neural nets. Okay, so if you take a step back, although the focus of this developer session and this talk is on neural nets, if you talk about automated machine learning is it encapsulates many different concepts. Feature engineering, if you are dealing with classical learning, for example, random forest and things like that. But let's focus on deep neural net, and within the deep neural net, so hyperparameter search is a subset of automated machine learning, and the neural architecture search is a subset of hyperparameter search, and particularly neural architecture search is for deep learning. And hyperparameter search, you can do hyperparameter search even for classical algorithms like random forest, gradient boosting, support vector machines, and so on and so forth. But again, we will be focusing primarily on machine learning, on deep learning, on deep neural nets. So the package consists of 3 different components. The first one is hyperparameter search. We have different algorithms. Asynchronous model-based search is the one that we will focus on, which is known as AMBS, right? There we have hyperband, and we also have evolutionary algorithms, genetic algorithms as part of this package. Neural architecture search is one in which we will define a sort of a high-level template, and the DeepHyper will go and try to find neural architecture based on the template. And the algorithm that we use for this purpose are reinforcement learning, and we also have aging evolution. It's a variant of genetic algorithm for neural architecture search, and we also have random search support. And in terms of workflow, because each of this thing, even if you want to evaluate one of them, it takes hours, if not minutes, right? And scaling this is necessary. Although in this talk, we will not be focusing on the scaling issues or how to scale them, because the scaling is already, if you are working, if you are going to do this on Theta, the package is available as a module, and you don't need to worry about that. The key ingredient for that is the Balsam workflow manager, which is sort of hides the complexity of scaling this on big machines. So we have integrated DeepHyper with Balsam, and the Balsam is responsible for taking different hyperparameters and evaluating that on different nodes of Theta and give the results back. Okay. So these are the 3 components, and we will be focusing on hyperparameter search and neural architecture search. Okay, so automated machine learning for deep learning. So there are, if you think about deep learning, right? So there is a lower level optimization problem, which is the training problem, right? So for a given architecture, you choose an architecture and you choose a set of hyperparameters for that architecture. Then given the training data, you go and adjust the weights of the neural network to minimize some loss, right? So that is the lower level problem shown here. And the upper level problem is finding that architecture space and the hyperparameter search. So the upper level problem is we are working one level upper from optimizing the neural net for training, right? So training loss, or minimizing the training loss. At the upper level, we are looking at, okay, so here is an architecture space, and here is a hyperparameter space, and we sample from this and then go on and train for this particular architecture. What is the loss? Okay. So what are the challenges? There are many challenges, right? So if you think about the hyperparameter search problem, so let's focus on that one as the first one. You have mixed integer, because the problem is, can have just not the real parameters, but integer parameters and categorical parameters. For example, type of optimizers, if you choose Adam, RMS prop, and so on and so forth. These are all discrete parameters that doesn't have any relative ordering. And even the integer parameters like batch size, they are not like 1, 2, 3, but you have 16, 32, 64. They are discrete, and they're a lot more harder. It's not integers from 1, 2, 3, 4, 5. Okay, and we have real parameters, which is like, we'll see what those are. And this is again, the problem is even made difficult by the fact there is no gradients, because so this is a black box optimization. For a given hyperparameters, what we have is just the validation loss from a neural network, and based on that we need to decide what is the next point or next hyperparameter configuration that we need to sample. So there are no gradients. And most importantly, why this problem requires scale, or why this problem requires clusters or supercomputers, is because if you try to do this on your own on laptop, you can do that, but it takes longer, right? So each evaluation will take several minutes, and you have to do that sequentially. But imagine if you have 1,000 nodes at your disposal, you can evaluate 1,000 configurations in parallel, get the results back, and the algorithm is capable of handling this type of scale. So the computational expensiveness makes this problem a high-performance computing problem. So some of the common methods people use, grid search and random search, they are not particularly way to go. If you are dealing with fewer parameters, and if you know those parameter ranges very well, if you already identified good values, then this is good. Grid search and random search is okay, but otherwise you need sophisticated algorithm to address this problem. So what are some example hyperparameters? Learning rate, it's a continuous parameter. Clip norm and clip value. So the top box, if you choose just an optimizer, you have to deal with like 7 to 8 parameters. For a given optimizer, you have 8 parameters. And then you have batch size, epoch, and number of units per layer, and so on and so forth. So you can, so this is to show that, there is a wide range of hyperparameters that you need to configure, when you want to target high performance or a high accuracy with a given neural net. So the asynchronous model-based search algorithm that we developed for hyperparameter search works as follows. So this is the high-level idea. So there is an initialization phase where the algorithm samples, let's say, 100 different hyperparameter configurations. So you have to define the space, and it will sample 100 different configurations. It evaluates all of them simultaneously on different nodes, and then get the results back. And this is asynchronous because some of them will finish earlier than others, because either you can make the batch size, or you may, if you build a much deeper network, it takes longer to train as opposed to smaller network, right? So this can introduce asynchronicity, and all of them don't finish at the same time. So the algorithm is capable of handling this asynchronicity. As soon as an evaluation finishes, it takes a result back and then generate another point to go and evaluate. So at the top level, what's happening is there is a learning model, another learning model that tries to learn the relationship between hyperparameters and the accuracy metric that we want to optimize. So here the accuracy is the validation loss. So we are not talking about the deep learning training. So after deep learning training, we will use a validation data to validate and get the accuracy on the validation data, and we give that as a response. So what the algorithm sees, the learning model here sees, is hyperparameters and hyperparameter configurations, and then their corresponding accuracy. So it will keep on evaluating that and then learn from this. There is a learning model that learns the relationship between these two, and then generate better configurations in an iterative fashion. So that is the second phase of the algorithm. So the initialization phase happens in the beginning. The iterative phase happens, each time when evaluation finishes, the model takes that result, refit, retrain it, and sample a new point. Okay. So the approach is very similar to Bayesian optimization. So Bayesian optimization. So note that the learning model that learns the hyperparameters and the accuracy, we cannot use deep neural nets because first and foremost we don't have a lot of data for that, right? Because we have to operate in this small data regime. And this whole idea of where to sample is based on Bayesian optimization ideas. So the little cartoon here shows how this thing happens. On the x-axis you have input, and y-axis you have an output, and the red points are the observations. So imagine that the algorithm already sampled those red points. So using the Bayesian optimization idea, we can exploit model uncertainty. So wherever we have points, we have the uncertainty very small or zero. Wherever we don't have points, the uncertainty will be higher. Now the algorithm is tasked with, okay, so here is the uncertain area, and here is an area where I'm certain, but if I sample, I have a little bit of little room for improvement. Now the algorithm needs to sort of trade off this thing. This is called exploration versus exploitation trade-off. Exploitation is, I know the region well, I want to go and sample there, versus, oh, I don't know the region. If I sample there, I will know a little bit more about that region. That will eventually help me to find better hyperparameter configurations. Okay, so all the Bayesian optimization search does is, trade off this exploration versus exploitation, and it uses some metric called LCB to find which point to sample next. So as soon as as at a given state t, if you have an evaluation coming in, then you use that point to sample the next point. Okay, so next we will focus on the neural architecture search, the most interesting aspect of DeepHyper. So the way that we define the search space for the neural architecture search is shown here. So we define some blocks. A block has several nodes, okay, and there is a cell C0 that encapsulates box and the connections. So you see, this is a sort of a meta template where you say, okay, my neural network is composed of nodes, blocks, and cells. And all you have to define is how the blocks look like. And then you say, okay, so this is how my blocks look like, and I need this many cells, right? So you can just repeat those blocks within each cell, and then now what we have to do is, for each of the node, we can define different choices. And the neural network has to go, neural architecture search has to go and figure out what is the right choices for each one of these oval boxes. Okay, so what is different, or what is critical here, is how these cells are connected. Okay, so one way is just simply connecting them one after the other, right? But we all know the residual networks, the very idea of connecting one part of the network to a different part of the network makes the training a lot more easier and makes the algorithm a lot more robust, and it addresses the vanishing gradient problem and so on and so forth. So the key aspect here is the neural architecture search has to figure out, okay, so I have two possibilities. Let's take C2. Okay, C2, I have three possibilities. Either I can connect directly to the input, or I can connect to the previous cell C1, or I can connect to the cell C0. So when you are at cell C2, you have these four choices to make. So your input can be your previous cell, or it can be the previous cell, or it can be the input. And this gives really sophisticated architectural possibility. And we can, as we will show, even for the simple example, the kind of neural network that you can construct with such a simple template is amazing. So we'll look into that. So what we do here now is, from the template, we have this neural architecture search. This is one particular instance of that template. So you see, now we filled everything. So N0 is a dense layer with 5 units and ReLU. Then it is followed by dropout with the 0.7. Then there is a concatenation. Okay, and then you see how the skip connection works. So from the third cell C0, we are taking the output of cell C0 and connecting that here. Okay, and this one gets an input, another input. So IS and I1. So either you can connect to this one or this one. So these are all we can define in the template, and it's pretty flexible. In the beginning, it might be little difficult to define this template, but we have defined some example template. You can start with that, and then you will get to understand how this template works, and then you will figure it out. It's pretty easy to define. So what happens? This is a one instance of that neural net. Okay, and then once you have the neural architecture, so this is a particular architecture, then what you do is you load the data, pre-process, train, and you give the objective. So objective here is the validation validation error. And then this goes in a loop, and the neural architecture search has to find, using this loop, the best, slowly improves the architecture that it generates. Okay, so there are two different approaches that we implemented. One is the reinforcement learning one, where an agent here, a reinforcement learning agent, which is basically another neural network, which basically makes a decision within that template. So, for example, one agent can generate this type of architecture, another agent will generate this type of architecture. Each agent will work independently, okay? And they sort of exchange their information through a centralized parameter server. So think of this as a neural network, and then this is another neural network, and the neural network is tasked with choosing different options for the template. And once you have the particular configuration, you go and evaluate that deep neural net. So this is a deep neural net, or this is a neural net that is generating another neural net. So that's a way to think about RL. And you have several neural nets doing this task. So you get the reward from each batch, and then you basically exchange those parameters. And you do that number of times. So what happens is the type of network that it builds slowly improves, and you eventually get a pretty high accuracy. So another algorithm is the evolutionary algorithm, which is particularly called, this particular algorithm is designed for neural architecture search. It's called aging evolution from Google, and we implemented that within DeepHyper. Here, the idea is, again, you start with the population, you do some mutation and evaluate the mutated network, get the reward, and put back that in the population. And you do that number of times to keep improving the population. Okay, and yeah, you kill the oldest one in the population. Yeah, that's it. So these are all the sort of high-level overview of the algorithms that are behind DeepHyper. And just to remind, what is this in terms of automated machine learning? So we are looking at the upper level problem. We are not looking at distributed training, or we are not trying to make the training better. But what we are trying to come up with is, okay, so how to find the best hyperparameters and how to find the architectures in a much more automated way rather than human trial and error process. Okay. Now a reminder: high-level overview, hyperparameter search, neural architecture search, and workflow. Workflow is very critical for scaling this on Theta. Okay. Some acknowledgements. Early career research program, Argonne Leadership Computing Facility, and the Argonne LDRD. Okay, so with that, I want to go and show you some examples which you can try yourself as well. So, you can go to DeepHyper documentation. Okay, so I need to share this. Share screen. Okay, so the DeepHyper package documentation is available here. I will enlarge this. DeepHyper, read the docs.io, or if you can Google DeepHyper, you should be able to find it. Or in the ALCF website, we have a separate page for DeepHyper package, and you can go from there. So here is the documentation, and we have install instructions on your local machine. Theta and Cooley, you probably don't need to install much, so this is available as a module. But the local instruction is pretty straightforward. Either you can do pip install DeepHyper once you create a conda or virtual env, and or you can do it from the source with the documentation and tests installed. That's it. So installing this is pretty straightforward, and for your local machine, it also installs Ray, which is another workflow manager, and MPI. So you can choose one over the other, how to distribute your multiple configuration evaluations. But I don't recommend you setting like 100 evaluations in parallel, because that's not going to happen on your laptop or on your desktop. Okay, so so if you go here, and I will be primarily looking at the developed version of the documentation, and this will be moved into latest, within a couple of days, or later today. But this, we sort of simplified a lot of these things, and here you can go to tutorials. You can try this yourself after following the install instructions. You can go to hyperparameter search. So let's first look at the hyperparameter search, setting up the problem. So follow those instructions, and we can do this here. Okay. So HPS demo is there. So I already tested that. So I'm going to do HPS demo 1. Can you see my screen? Is it visible?
Yeah.
Okay, great. So I'm going to do HPS demo 1. So if you do DeepHyper start project HPS demo 1, this is a TensorFlow warning. Don't worry about that. I will address that in the next release. So this is now installed. So if you go to HPS demo 1, okay, so now you have a package in it and setup. So you can set up the problem, and you can install this problem as a package, so that when you are doing that on Theta, it is much more easier to find and use this problem. Okay, so once you do that, we can create this particular problem set called polynom 2. So polynom 2, I will show you. It's just a test function. Polynom is a mathematical function. You can see the formula there. So it will create some templates. So you see, if we do DeepHyper new problem HPS polynom 2, it created this directory polynom 2. If you go to polynom 2, okay, it will see 3 files. So this is how you create your own problem, one hyperparameter search problem. You can just take this and modify. I would highly recommend doing that as a starting point. You will see 3 files created, and 3 files are already, like, these are not empty files. Let's go and see what are they. First, see code load data. If you look at what the load data is basically a function, okay, that generates data using this polynom function. Okay, so polynom is a mathematical function. It just creates data and split them into training and testing data. Okay, here you can replace the polynom with your own training data and testing data and just return them. Okay, and what you see here, yeah, so load data is a function, and it has some parameters, default parameters, and we generate the train, we generate the test, and we just print them. And you can go and see how this looked like. If you execute that. Yeah?
We have a question.
Yes.
Alfred is asking, does the network topology of the supercomputer have to be set up a certain way to do neural network machine learning?
No. These are all already taken care by the Balsam. So you don't have to worry about how you distribute the job on Theta.
Thank you.
Okay. All right. So what you see here is, it's basically that function loaded training data and gives the training data and test data, right? So the training data is the one that you will train on, and the test data is the one that you will evaluate that network on and give that evaluated value. For example, R squared is a metric that you can use for the regression problem, and return that to the hyperparameter search. Okay, so we'll see how to define that. But let's say, a load data function is just loading the data and returning that. Okay, great. So if you go to the next one, code model run.py. Okay, so this is another file in which we define a model. Okay, so here is a model that we define using Keras. Okay, so here is a simple model. You have model sequential, and you just do a dense layer, which takes the number of units in that layer is given by the point of units. Okay, this is a dictionary, and activation, again a hyperparameter, and the input shape is directly received from the training data. You see the load data that we defined in the previous file, it is called here. And then you just define a simple network here, and then you compile the network, you do the model.fit, and you return the validation loss, right? So validation loss on the R-squared. And this is a standalone module, right, which just called the load data. And then as a default, we gave like 10 units, ReLU activation, learning rate 0.01, and then let's execute that. So there's no hyperparameter search. We just define the model and we run the model. You see, so this is one. So it has an early stopping criterion, but the point is now it evaluated one configuration, and then it is going to do the next one. Okay, so it finished all of them. Sorry, it was fast. Oh no, sorry. This is one network, right? So there is no hyperparameter search. We ran that network, and here is what the validation or how the learning looks like. So the R-squared value of 0.0148 for that simple network, which is pretty bad. And R-squared of 1 is pretty good. R-squared of 0.148 is pretty bad for this simple network for this default configuration. And what you see here is how the network trained. Okay, so now let's go and define the problem. So the problem is basically, we made the units, activation, and learning rate as sort of the arguments, right? So to define a hyperparameter search problem.add dim units, you say 1 to 100. Dimension, again, activation, ReLU, sigmoid, tanh. Learning rate goes from 0.001 to 1.0. And then, so here is, you say starting point. The starting point is the point that the search will start with. Now, once you do that, so once you define that, then, there are imports. You can see the example in the import. So the problem is essentially defining the search space. So once you define the search space, you can go and run the hyperparameter search. You can go through the documentation as well. Basically, this is what we explain here. Running the search locally is simply this command, where DeepHyper, HPS, hyperparameter search, do AMBS, asynchronous model-based search, problem is polynom2, problem, and run the model.run. So this is the command line parameters to run the hyperparameter search. Okay, so now let's run that. You see, so it is evaluating configurations that are pretty bad. R-squared of, you are seeing R-squared negatives, right? So that's here. So it finished one of them. Now it is doing the next one. We are doing sequential, right? So we are not doing multiple at the same time. So here we are doing sequential. But you will see, the R-squared were pretty bad before. Now it's slowly improving. Now it is in the negative something. Now you will see it slowly gets to 0.9. So remember the initialization mode. So now it has sample configurations at random, and then it is trying to learn the relationship between these three hyperparameters and the validation error. Now you see the R-squared has already improved to 0.8. Okay, so yeah, it will eventually go to 0.95 or something like. You can already see it's 0.9. It's already hitting 0.92 here. Okay, so let me stop this and go to the next one. This is the neural architecture search. So new problem. So I'm going to create another project called NAS Demo 1. Okay. Again, you can see inside NAS demo, init.py setup.py to make this as a package. And then I'm going to create a NAS problem now with the polynom 2. Instead of HBS, I'm going to say NAS polynom 2. That will create the template files for you. Okay, so you see here it has created a polynom 2 directory for the NAS. Now, see the load data that we have, it's the same. Okay, it just loads the train data and returns the training data and the validation data. So you can execute that and see Python load data should give you the training data and the validation data. Okay, so there are 10 inputs and 1 output. We have 80K training data and 20K for the validation. Okay, and so here is the template definition. Okay, and the template definition you can see. So you can look at the code. So essentially, what the template definition is all about is we are defining several nodes. Remember the nodes. We don't have cells and blocks. To make it really simple, we don't have cells and blocks. We say, okay, here is my node, and you say how many nodes you want, and within each node you have several choices. Okay, one is identity. Either you can choose identity, or you can choose the number of units, 16 units with TensorFlow or with the ReLU activation, or with the TANH activation, sigmoid activation. Similarly for 97 units, 16 units. Okay, so this goes in a counter of 16. So 16 to 97, you do this. Okay, and each within a node you have that many choices to make. Okay, and then you repeat that node number of times. And you also, so this code, this piece of code is simply the way to express this search space. So at a given node, you have several potential connections. So, you are connected to the previous node. So the previous node is the output of the previous node is connected to the current node. Okay, but you can also have other skip connections coming to this node. The potential skip connections are, because this is already connected, you don't need to worry about this. Either you can connect to this guy or this guy or this guy. And there are also methods to say how you want to be connected. You can just take the output from this particular node and then do a concatenation as sort of the input to this node. Or you can add them by padding. You can do a zero padding and then make them, both of them equal, and then add them. Or you can also do some sort of linear combination. Okay, so so these are the different ways that you can do. You can sort of do the skip connection. So this piece of code is exactly doing that. If you just follow the code, you will see, oh, so this is like keeping track of how many previous nodes I have, and then making them as a sort of a placeholder for skip connections. Okay, so that's the search space definition. So it's pretty much what I showed. It's pretty much what I showed here. And then what you have is the problem.py, which is basically saying that for the hyperparameter search, we are fixing the hyperparameter. For the neural architecture search, we are fixing the hyperparameters. Okay, we say, okay, these are the hyperparameters that we were fixing, and we want to go and minimize something. So mean squared error is the loss, matrix is the R squared, and we are looking at the validation R squared of the last epoch, because we have early stopping criterion. So we don't want to see a loss or a validation R squared that peaked some point of time, but towards the end it reduced, because that is more fitting. We don't want that side of network. We want to optimize with respect to the last R squared value, because that's much more robust. Okay, so that's it. So the problem is defining the hyperparameters and then say what is the loss that you want to minimize. So you can use any string of the keras or the TensorFlow. So this is directly we are basically inside using keras. So if you pass this argument, or you can pass your user-defined argument, whatever the keras will take as a loss, we can pass it here, and then the metric is R squared, and so on and so forth. Okay.
Prasanna, we have another question.
Yeah.
CV is asking, can load data.py return data of any shape?
Yes. It can be any shape. It doesn't need to be this shape. It doesn't need to be this shape. So all the load data does is, it returns the data in as a tuple, and it's entirely up to you to, as long as the data is defined. So if you see here, the input shape and output shape, these are placeholders, okay? And as long as the input shape and output shape are determined from your load data, then that will be passed as an argument here automatically. So yes, you can pass any, you can do a 3D tensor, for example. It doesn't need to be this 2D. Okay.
Thank you.
Great. So we can, so these are the only three things. So load data is the same, problem.py, search space is the template that you need to define, but I would strongly suggest using the template that we have here as a sort of starting point, and then you can go from there, trying to build a lot more complicated, sophisticated template based on your problem. But for tabular data, multiple input, multiple output, you can start with this, and possibly you can see some good results. So one thing you can also do Python search space.py, and then generate one sample from the template. Okay, so you see we have a sample network here, and you see how with that simple template, this is a one particular neural architecture in that space. You see, this is pretty sophisticated, right? So the template is simple. We just define the number of nodes and different possibilities, and if you just sample from that, thanks to the skip connections, you can build really sophisticated network architecture. Okay, and then so this gives the flexibility, right? The space that you want to search is rich enough. Now it's up to the reinforcement learning and the genetic algorithm or the evolutionary algorithm to figure out which is the best one. So all we have to do is give enough a rich sort of search space and let the search do the work for you. Okay, so what we did is just a particular sample from that space. If you just run that. Okay, now we want to go and run neural architecture search. So if you go to the documentation, neural architecture search. So here we will be using .py. Okay. It's a simple one. Again, here evaluator equal to Ray. So Ray is another sort of a workflow manager, which we also integrated here. So this is just to demonstrate that, we can, on a local machine, you can use Ray. And if you have a cluster in your university or in your particular facility that doesn't have a good workflow manager like Balsam, first try to install Balsam. If that doesn't work, then try to install Ray, because Ray has a lot more sort of flexibility in terms of support and things like that. So so here is what we do with the oh wait, sorry. That's one. Demo one. Oh, sorry. This should not be here like this. Okay, we define only polynomial 2. Okay, it's start running with array backend. You see the architecture that it came up with, just without using any hyperparameter search, we just provided the rich architecture space, and within a few evaluations, it's already hitting the R-square of 0.99. So that's the sort of power of neural architecture search. If you provide rich architecture space then we can do a lot better, and we don't need to go take this trial and error route to find out, what is the best architecture for this data set, and keep on doing that, this manual process of going back and forth and running them. So the real power of DeepHyper is when this is run at scale, when we have hundreds of nodes running in parallel, evaluating configurations or evaluating architectures in parallel, and giving the results back to the reinforcement learning, and allowing them to learn how to build these architectures automatically.
Thank you all for attending our dev session today. If you have suggestions or questions, please let us know at devsessions@alcf.anl.gov. And with that, thank you all.
Thank you, everyone. Bye-bye.